Hello, hello, hello.
Okay, we'll start the class. Tomorrow is a full break, so we'll have fewer attendees today. Last class on Monday, we stopped here at the ANOVA test for numerical variables, and it gives us the F score and the p-values, and to examine whether there's a significant difference between the two groups of the means and the variance. And if the p-value is smaller than 0.005, then that means we reject the null hypothesis, and which means that there's a significant difference between the groups. So here, do we need to remove any of the numerical variable? This is the p-value for all these 5 numerical variables. Do we have to remove any of that variable here?
The fourth one.
The fourth one, no.
Yeah,
this one, it's smaller. It's smaller than the 0.05. So which one? Which one the difference between the two groups is less significant than the others? Which group is less significant? The highest p-value. This one, yes, it's almost close to 0.05, but still it's smaller. So the difference between the two groups is significant. This one, this variable. So if the number is larger than 0.05, you should consider removing this numerical variable. And same with a categorical variable. So let's generate this counterplots again. We'll look at this plot. For this variable, they have this almost the same proportion. For each group, there's almost the same proportion of people had attack and had no attack. Right? Almost 2 to 1 and 2 to 1, almost the same proportion. And for here, sex males has the larger probability to get heart attack. And then same with this group. This group, the group 4 is the more likely to get heart attack. And we also have, we can also use a test called a chi-square test to verify this. So how does this chi-square value work? It's the computer will calculate for us, but we need to know how it's calculated. Heart attack, female and male. If there's no significance between these groups, male, female,
If there's no significant, this is 2 to 1. Okay. Oh, this is 2 to 1. If there's no significant difference between male and female, how this should look like? How this one, the last bar, how this should look like?
The same proportion.
Actually, the same proportion, right? 2 to 1. So it should be like this. It should be like this. So that's how the chi-square works. So it calculates here the number of female has a heart attack and no heart attack, and the males has a heart attack and no heart attack. So we get the total population. So this is 14, and this is 27. And then the total population is 41. And within these 41, within this total population, in this total, the entire group, how many had a heart attack? It's 18 people had a heart attack. And then no heart attack should be 23. If there's no significance between these two groups, they should keep the same proportion as the 18 to 24, 23, right? Like this. It should keep the same proportion if the same ratio if they has no significant difference. So that should be this expected. Let's do this. 18 divided by 23. So I'll name it R. Okay, ratio. Okay, ratio. So if there's no significance for this group, then it should keep this ratio for heart attack and no heart attack. Okay? So the number of female had a heart attack. What should be the number of female had a heart attack? It should be not 6. Okay, this is the observed value. We call observed value, and this expected value. This expected value should be the number of female, and then times this ratio. Right? If they have this group had no difference with the male or with the whole population, then it should keep this ratio. They keep this ratio 18 to 23, and then times the whole population, the whole female population 14. Isn't it? So it should be this expected value. This expected value should be 14 times this ratio 18 divided by 23, and this one should be 14 times it should be if it's 18 to 23, then no, it's actually 18 to 41. Sorry, the wrong. 18 to 41 is the percentage of people get heart attack, and this one should be what should be this number? It should be 14 times yes, correct. 23 times 41. Okay, and the same we can get the males population who expected number. Okay, expected number of I guess we get here now. So this chi-square, it calculates the difference between the observed number and the expected number. If this observed number is the same as the expected number, what does that mean? If the expected number is the same as the observed number, that means that it keeps this percentage. It keeps this percentage, and it has a 41. Okay. It matches to this percentage. If this number is the same as this one, it matches this percentage, 18 times 41, divided by 41, right? So there's no significant difference to the population. But if this gap minus, okay, minus, if this gap is big, that means there's a difference, significant difference between these two groups. So it added this gap together, added the difference together, the difference between, well, for this group and the difference for this group, add all these difference together, that gives you the chi-squared value. The larger the chi-square value is, the more significant the difference is. Did we get it? Okay. So actually, it doesn't calculate the minus, but it calculates the square value. So it's how it calculated the observed value minus the expected value, and then as a square. And it should be a relative number, so it divided by the expected value. Okay, and then add all these the numbers for all these together. I get the chi-squared, the eventual chi-squared number. We need to understand how this works, how this test works, and then the value. We really don't need to calculate it, and we can use this select k best, this method, and we give it to the x. Y should be the target variable, and the x should be the categorical variables, and it tests whether these x has different has a significant difference. That gives you a score, a chi-squared score. And it gives you a p-value. So here, for the chi-squared score, which one has the most significant difference between the groups? Which one?
The last one.
No, there's a number.
Oh,
There's a number here. Yes. Yeah, but the larger the chi-square score, the difference is more significant between them for that feature. Okay, and also same with the p-value. If the p-value is smaller than 0.05, then we which means we rejected the hypothesis and null hypothesis, and we accepted that there's a difference between this variable is influential for the target variable. Okay, so here, is there any value larger than 0.05?
0.7.
Yes, 0.75. So what does that mean?
There's a large difference.
There's
a
no-
significance.
No significant difference. Yes, the p-value is too large.
it's larger than 0.05. So there's no difference for this between the groups, between these groups. Okay, for this. That means what shall we do next? Yes, jobless. Jobless column.
So we have to do is to job this column. Always verify the result after you finish one step. Okay, yeah, we did job this. Okay, we did the job this variable. Okay, good. Okay, the next thing we are going to do is to deal with the categorical variables.
We already mentioned, you already tried at your last assignment. For the categorical variables, we need to transform them into dummy variables.
So
Technically, these are variables that like this variable, it's already 1, 2, 3 now, but you cannot use these numbers directly, right? They don't mean, hey, this is higher than this one, 2 is higher than this one, or 3 is higher than 2. No, that doesn't mean, they just represent different groups. Okay, also I want to mention, so like for the p-value, for the ANOVA test and the chi-square test, some of the, if you read some like cases, some data report online, they may tell you just to, in some of the report, they just use a chi-square, this function for all the variables. Technically, it will still give you a number, because they just calculate based on these numbers. It will still give you a number, but I don't think that's a correct way, because let's calculate the, this is designed for the categorical variable, and the ANOVA is designed for the numerical variable. So you should do the feature selection step differently for numerical and categorical variable, not to apply the chi-square for all the variable, or apply the ANOVA for all the variables. It gives you a number, but that's not a correct way.
Yeah, next is getting dummy variables. So dummies, and you give it the data frame, and then you specify which columns you want to transfer to dummy variables. So here, we have to pay attention to this one, drop first. The first, what this means is that you drop to the first option in the variable. For example, for sex, it's 0 and 1. You don't need two column. You don't need two column like female, females 1 and the males another way, another column like 1 to represent the data. So this is sex. Okay. So if we change it to dummy variables, do we need to change it to two columns, one for female, one for male? We need to do that. If I show you this female 1 1 1 0 0, and then you change this, you do this column. If you change it to two columns, and then you do this to 1 1 0 0 0, that's redundant. Redundant. This female could you wipe this one. So we wipe this one. This is redundant. So this it could be merged to one column, and just this one represent a female and a male. Usually, if this variable only have two values, if it only has two values, you actually don't need to change it to dummy variable. You use 1 to represent the female, and then you use 0 to represent the males. So we can already tell what sex this person is, even without this one. We can tell. These zeros represent males. You don't need another variable to tell these are males. This one, 0 0 already represents male. That means the drop first. You drop the first value. And if it has multiple variables like a CP, okay, CP has 1 2 3 4, and then you got to CP1, you change it to CP1, CP2. CP3. CP4. And it's the same. So you use a CP2. Okay, CP2 is this is 0 and this is the 1. Yeah, this is a 2, right? This person is belong to the group 2. So and this is 0 0, and the CP3 is a 0 0 1 0, and the CP4 this is a 1. So this is this person. This you can tell this person. You can tell each person. This one is the CP value is that's 4, CP4. Okay, and this one, this person, the value is CP3, right? This CP value, let's say
And this one is the 1, so that means that the value is the 3. Another one, that means that the value is CP2. How about this CP1? This, no. How about this first person? First person, 0, 0, 0. Do we need another one to, do we need another column 1 to represent this? 0, 0, 0 just means that it doesn't belong to any of the group. It's a CP1, right? This value is a 1. So you can reduce the dimension. Instead of using 4 variables, 4 dummy variables, you only use the 3. You can save 1 column, reduce only 1 dimension.
What about null value?
Uh,
What about null value?
yeah, all 0 means that if it's all 0s, it means that it's the first group.
I mean, null value might be general in every CP2, CP3, and CP4.
Oh, what do you mean?
No,
No value.
yeah, null value. If
Ah.
if CP have null value, then null value might be 0, 0 in every CP2, 3, 4. Isn't it?
You mean if there's a case that is a null, if it's null, it should be removed before this. It should be removed. The 4 values. So usually if it has 4 unique values, it uses the 3 columns. And if it has three values, unique values, then it uses 2 columns. And if it has 2 values, female, male, you don't need to change it. It still keep just the 1 column to represent whether this person is female or male. So usually we set this job first to true. Okay, this parameter to true. I believe I need to reassign it. And then you verify this data again. So next we are going to split the data and split the data and then balance the data. So both are changing the entries. Both are changing the entries. The one is splitting the data into multiple data sets, and the second one is adding samples into it or reducing the samples into it to balance the data. So these 2 steps, which one should go first? Which one goes next? Usually we split the data first and only balance the training data. So when you balance the data, like oversampling, there are we can talk about balancing the data first. We mentioned balancing the data. What does balancing the data mean? Sometimes the target variable, there's a lot of people had a heart attack, but no people like a lot of people had a heart attack, and there's a very few sample with no heart attack, then affect the accuracy for that group. You cannot predict that group accurately. So you need to add samples into that group, right? That's called balancing the data. When you balance the data, you add samples into the data, or you remove samples data. You are changing the originality of the data set. Usually, we split the data first and only balancing the training data. We keep the originality of the testing data.
Well, we want this to be we want this to be original, to be accurate, not fake the data. And when you balance the data, you are adding it to it, you're manipulating it. So usually it's recommended splitting the data first and then balancing only the training data set. Okay. Yes, so now because we have the XY, you need to, so it's a X train, Y train, X test and the Y test equals the method train test split. So I import the library. Okay, I already import. And then you give it the X and the Y you want to split, and then the test size usually is 0.2, and you keep 0.8, 80% of the data to the training data set. And then there's one new parameter, or we have to specify here. Random state, yeah, random, I forgot the random state. This one, you don't have to do that for linear regression, for the numerical. If the target variable is numerical, you don't have to do that. But if here then the target variable is a categorical, we have to specify that, stratify, which means when you split the data, you want to keep the same portion, same proportion, same ratio of people heart attack and non-heart attack into the data set. So for example, we have one. We have in the original data set, we have 8 people had a heart attack and 2 people had no heart attack. When you split the data into, so 4 to 1, right? 4 to 1, had a heart attack and had no heart attack. No, okay. When you split the data into 80% to 20%, right? 80% of testing data. Okay, let's do 80. Okay, 80 people. And when you split the data into 80% and to 20%, you want to keep this ratio 8 to 2, right? 4 to 1. So you don't want to, hey, when you split the data, okay, all these samples go to the training data set and all these 20%, 20 people go to the testing data set. Then it will not work. The model will not be correct. So you want to keep the portion that 60 people go to the training data set, and then it's the 10. Yeah, I did the wrong number, but you see, we want to keep this ratio in both data sets. So that means that it has to stratify according to this ratio. Okay. That's what this parameter does, to keep the ratio, the same sample ratio in both training and the testing data set. But with the linear regression or with the numerical target variable, you don't have this problem. is splitting the data. And then, yeah, after each step, you check whether your answer is correct, whether the result is correct. You check the shape and to see if the training number of rows of the training data set is the same as then these two should have the same rows and these two should have the same columns.
Training and no, yeah, why? So these two should have the same number of rows and
These two should have the same number of columns. You need to check the shape and to make sure the number of data in each data set is correct. Okay. Next is balancing the data set. So there are two methods to balancing the data. One is called undersampling, and the second is called oversampling. What does the oversampling do? What does the oversampling do? So sometimes we have sufficient data, then we can reduce the one of the one group. Like we had thousands or 10,000 data. Okay, I don't mind reduce some of the entries for in one of the group. Okay, the minority group, the minor group. Oh no, the major group. The people with the group with more samples. I don't mind reduce some, and that's called undersampling. So oversampling means that you add data. You add data to this. This one, we have only 20 samples with no heart attack. So you add to it to make it 80. That's oversampling. And if undersampling, then you reduce this to 20. And you call this method SMOTE. This is usually the algorithm for oversampling. But if it's if you want undersampling, you have thousands of entries, thousands of sample instances, then you can do undersampling. It's another method. Okay, this method is only for this algorithm is only for oversampling, to add instances, to add entries. You see, they added 52 instances to the training data set. Okay, now I think our data is ready to do to apply the logistic regression model. And also make sure that usually at this step, you also make sure there's no correlation between these numerical variables. So you use the correlation to check if there's any correlation. Features with high correlation should be removed in such case. Okay, really, it's the same as we did for linear regression. Okay, model logistic, and you call this method call this algorithm. Yeah, put it here. And then you should use this model to train the data. So X should be oversampled. X should be the oversampled data. And the Y should be the oversampled Y. And then you, I think that's all we need to build this model. Okay. Oftentimes, it will give you a warning when your data set is large. It may give you a warning that the total number of iterations reach the limit, and then I will change the max iteration. So I will change this. The default value is 100, and sometimes you just need to change it to the bigger number to make to help it to iterate over all the cases. And then you can use this model to predict the data. The predicted data is X test. Predicted. Object is not called. Oh, okay. So that gives us the a group of the predicted number, and then we had the group of the observed numbers, right? Then we can compare the accuracy, whether how many did predicted correct and how many predicted incorrect. And that gives us the accuracy score. Okay. Can generate the accuracy score with the Y predicted and the Y test. You have to import another. You have to import another another method here. I believe I didn't import it. So here you have to import this accuracy score. Give us the accuracy score. Okay, 0.79.
Not too bad. So 0.9, of course, if it's over 0.9, it will be perfect, but 0.8 is not too bad. And do we understand how this accuracy score we got? How we got this accuracy score? You compare the predicted number to the test number. So if it's correct, okay, a correct case, and then it's divided by all the cases and to get how many cases were correct.
And if we plot this confusion matrix called confusion matrix, you give this the model you just trained, and then you give the testing set to this method. Then it will give you matrix. What does that mean?
Which ones are correct cases? Which ones are incorrect cases? It's the observed value, and this is the predicted value. So for in the square, this one is it was 0 for the observed, and it's predicted 0. So this is correct. And this one is also correct. It's observed as 1, and it's predicted 1. So this is also correct. These are wrong cases. Predicted 0. It was 1. Same with this. So the accuracy score should be how do we get the accuracy score? Which number added together and divided by which number?
You add the predicted and the test.
Which number? Tell me the numbers
Oh.
here.
The just the 0 and the 1.
Yeah, so the accuracy score is the correct cases divided by all the cases. But here, which number represents the correct cases?
42.
Yeah, 42. It should be, these are the correct cases. It's observed 0 and predicted 0. So observed 1 and predicted 1. So these are the correct cases, and these are the wrong cases, predicted not wrong.
The accuracy score should be 26 plus 16 divided by all these 4 numbers added together, all the cases. Okay, it's an accuracy score.
There are other methods to evaluate whether the model is good or not, but this is the commonly used score. Okay.
Commonly used ones. Okay, then with this model we built like the linear regression we did, or you can obtain the intercept and the coefficient numbers. So, print intercept. Mhm. It should be the oversampled X. It doesn't matter. So you got the numbers of the intercept and the coefficient, and if you ask you to write out the formula, you should be able to do that, right? Or we learned the probability equals so the probability should be equals 1 divided by 1 plus E AX plus B. So here AX is the age, B is the intercept, B is the intercept, minus 0.1, and then you plus AX, we link 0.044. This number times the age, and then you list out all these variables. Just list out all the variables, and that gives you the formula to calculate the property. Of course, we don't need to do that. You just can use the predict to predict any case you want, any new case you're given. Okay, that concludes this module about logistic regression, and in the assignments you have a similar case like this. Yeah, so you have to walk over the code by yourself. Okay. Any questions about the lesson? Yes. What's the problem?
It's like the problem with one of the endpoints for the
Oh, okay.